that we've almost completed kind of our catalog of functions we are able to differentiate. We know how to differentiate powers. We know how to differentiate trig functions. We know how to differentiate e to the x, although we'll talk more about that today. And we're going to finish off our list by figuring out how to take the derivative of the natural log of x, and then eventually the inverse trig functions. And then that's kind of everything. Those are really all the functions that we have that we're, and then just combinations of them. So products of them, sums of them, quotients of them. But at the very basic level, those kind of 8-ish things, well, plus a few more if you type inverse trig, are all the things that we talk about, all the functions we talk about differentiating. But what about the natural log of x? Today is what? The 15th. Apparently it's Singles Awareness Day. Seems kind of messed up that they make the acronym for that what it is, but okay. Anyway. Yeah, right, exactly, right? It's like seasonal affective disorder too. I mean, really, you couldn't come up with something that was just less cruel. Continuing on. We want to find the derivative of the natural log of x. And I'm actually going to talk about this in two different ways, just so that you can kind of see, well, so that we can do it in a way that doesn't depend on the first way I'm going to do it. So here's the first way of doing it. We're going to start off by writing it as y equal to the natural log of x. And then we're going to rewrite this as an exponential equation. So instead of y equal to the natural log of x, our base e, which I didn't write there, raised to the y power equals x. And this is one of the reasons we just spent some time talking about implicit differentiation. Because now what we're going to do is we're going to differentiate both sides. But we're going to remember that literally we just were saying that y was a function of x. So when we differentiate e to the y, it's like we're differentiating using the chain rule. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff, which you can either write as y prime or as dy dx. On the other side, the derivative of x is just 1. If you really like, you could have written this as e to the y times dy dx equal to 1 times dx dx. If you really want to think about why we're not writing anything else there, it's because dx dx is just 1. There's no chain rule to use there because the variable is the variable that we're differentiating with respect to. And then if I want to solve for dy dx, I'm going to divide both sides by e to the y. So that dy dx is equal to 1 over e to the y. And then, since we know that e to the y is equal to x, we're going to rewrite this as dy dx equal to 1 over x. So, our function y equal to the natural log of x, the derivative is 1 over x. The derivative of the natural log of x is in fact 1 over x. Now, you might ask yourself, well, how would we do this if we didn't know that the derivative of e to the x is e to the x? Right, so we definitely relied on that fact to do this. Well, we could do this the limit differential, the limit, oh my gosh, the limit definition of the derivative way. It relies on something that we kind of talked about when we did the derivative of e to the x as well. So I want to remind you is probably not the right word. I'm going to tell you about a limit that you might have seen before, but you might not have seen before. So note or observe. And again, all this we're about to do is maybe not the most important thing ever, but I want you to see it so that you have this idea a few different ways. The limit as h approaches 0 of 1 plus h to the 1 over h is in fact equal to e. True story. You could make, in fact, I think we talked about last time looking at the graph of this. I think we pulled it up on Desmos and saw that as the values of h get closer and closer to 0, like if h is, for example, 1/2, 1 plus 1/2 to the second power is equal to 2.25. And if h is equal to 1/4, you know, I don't actually know the numbers off the top of my head, so let's actually pull up Desmos, because use the tools you've got. Maybe. Can I use h's here? Probably. So if we do y equal to 1 plus h to the 1/h power, and we start plotting some values, if h is 1/2, 2.25, and if h is 1/4, 2.44. If h is closer to 0, we're getting numbers that are closer to what? 2.7? 2.7 something. So do we get closer to 3? That doesn't look like it. Looks like I'm kind of stuck. No matter how close to 0 my h values are, it looks like my 1 plus h to the 1/h is 2.718281828, which is getting closer and closer and closer to the irrational number e. So it is worth knowing that, yeah. Oh my, smart, real smart. Sorry, one sec. Of course, it never wants to, there we go. So that as the values of h get closer and closer to 0, the values of 1 plus h to the 1/h get closer and closer and closer to e. So there's, oh no. There is a way of proving this limit, like this limit here, but it requires L'Hopital's rule. So later on at the end of the quarter, when we talk about L'Hopital's rule, we'll revisit this and talk about how you can show that this is 0. I will also point out another way of writing this that's equivalent is the limit as, pick whatever letter you like, as n goes to infinity of 1 plus 1/n raised to the nth power is also equal to e. Basically, if you have 1 plus something small, something getting close to 0, and the power there is the reciprocal of that thing, then the limit of that is always going to be e. So 1 plus a small thing raised to a large thing, as long as those things that I've just said are reciprocals, the limit's going to be e. So I'm going to mix it up just a tiny bit here. You always not want to go away. Sorry, one sec. Let me move this around and then move it back, and then magically it wants to disappear. Okay. So more generally, I'm going to write this and watch this for a second. Instead of 1 plus h to the 1/h, I'm going to say I have the limit as h goes to 0 of 1 plus h over x raised to the x over h. I still have the same sort of situation. H is going to 0, so as long as x isn't 0, which it's not, h over x is getting closer and closer to 0, and x over h is the reciprocal of that, and that limit is going to be e. Okay, here's why we needed that. Now we're going to find the derivative of the natural log of x using the limit definition, and we're going to use that limit that we just talked about. So the derivative of the natural log of x using the limit definition is going to be the limit as h approaches 0 of f of x plus h, which will be the natural log of x plus h minus the natural log of x all over h. And then we're going to use one of the properties of logarithms that says if you have a natural log, or any base really, a log with any base minus a log with the same base, we can do the logarithm of the quotient. So it's going to equal the limit as h goes to 0 of the natural log of x plus h divided by x. All divided by h. I'm going to use a little bit of rewriting, which might seem a little out there. I'm going to write this as the limit as h goes to 0 of 1 over h times the natural log of x divided by x is 1, and h divided by x is h divided by x. So far, not too bad. Here's the part that always feels like someone's just making stuff up. But what we're going to do is, what I really want to do is I want to make this appear. I want a 1 plus h over x to the x over h power. So what I'm going to do is I'm going to put an x over h in front here so that I can use the log rules to bring it up to the exponent there. But if I'm going to multiply by x, I also have to divide by x. So I'm going to rewrite this as the limit as h goes to 0 of 1 over x times x over h. Right, just multiplying and dividing by x. I'm not changing anything. Times the natural log of 1 plus h over x. Finally, this x over h, I'm going to bring up as the power of the thing that we're taking the natural log of. This is the limit as h goes to 0 of this 1 over x still stays in front. And now I've got the natural log of 1 plus h over x to the x over h. I feel like I'm something. Oh. Did I lose something here? Sorry, my brain is missing something. Yeah, what am I missing here? Sorry, I'm just like. So here's what I know the answer is supposed to be. I know the answer is supposed to be 1 over x. But if I took the limit now, I'm really missing it. I found my mistake. So here's the I didn't say any words. You guys are like, what's he talking about? He says there's like, so what I thought, what was missing in my brain for a second was I was missing that natural log. And so I thought I was going to take the limit of this and just get e. And then I was going to get 1 over x times e, which wasn't the right answer. But there's actually a natural log there. And so if I bring this limit inside, I get 1 over x times the natural log of the limit as h goes to 0 of 1 plus h over x to the x over h. Well, the limit of this is e. And so we're going to end up getting 1 over x times the natural log of e, which is just 1 over x times 1. So the derivative of the natural log of x is indeed 1 over x. And then if you really wanted to, you could use this derivative to go then show that the derivative of e to the x has to be e to the x. So I know there was someone, I don't remember who, was asking me why is the derivative of e to the x just e to the x? And I was like, well, we did the limit definition a while ago. And I will admit it was a little hand wavy. That limit definition always is a little hand wavy. But now this one feels a little less hand wavy, in my opinion. It feels fairly solid. And then if you wanted, we could say, well, using the fact that the derivative of the natural log of x is equal to 1 over x, we can then find the derivative of y equal to e to the x. And the reason I'm writing is y equal to e to the x is because I'm going to take the natural log of both sides. So I'm going to rewrite this as the natural log of y equal to the natural log of e to the x, which just becomes the natural log of y equal to x. We're going to take the derivative of both sides. Again, making the assumption that y is a function of x. So when we differentiate the natural log of some stuff, it's going to be 1 over the stuff times the derivative of the stuff. On the right-hand side, the derivative of x is 1. Solving for y prime is equal to 1 times y, but then substituting back in what we said y was equal to in the very beginning, y prime or dy dx is equal to 1 times e to the x. So the derivative of e to the x is e to the x. Cool. And then of course, just like with every other function we know how to take the derivative of, there is a chain rule version of it. So, no, sorry, papers are all over the place here. So these, I know one of these rules we already have, but I'm gonna say it again. The derivative of e to the x is e to the x, and the derivative of e to the stuff is going to be e to the stuff times the derivative of the stuff. And similarly, the derivative of the natural log of x is 1 over x. And now we can also say that the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Or people often write, although I don't usually, the derivative of the stuff divided by the stuff. I really like the doing the rule and then at the end thinking of multiplying by the derivative of the stuff. It keeps it more clear in my mind that we're doing the chain rule. But if you want to write it a different way, that's also really fine. Cool. Let's do some examples. Unless you have any questions. Like you all, I mean, you guys know, but I'll reiterate, blanket statement. You're always welcome to ask questions, right? If you have questions, you should ask them. Sometimes people come up to me at the end of class and they ask me something. I'm like, you should have asked this so everyone could have heard your question because everyone would have liked to have known this. So please, 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 if you have a question that you're saving for the end of class or you think, oh man, I wonder what's going on there, just ask it. I'm really happy to clarify, happy to talk more. Obviously, I'm happy to talk, right? Talking. I would love to give you all more of an opportunity to do things, but the hybrid nature of this, I feel like, doesn't allow for that as well. So, all right, let's do some examples. So, and I'll ask you when we get there. So, what about the derivative of the natural log of sine of x? Well, usual deal. Derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of the stuff. Normally, I wouldn't simplify. Here, I would make an exception and say, oh, that's really cosine divided by sine, which is going to be cotangent of x. Later on, when you're taking 21B and someone asks you what's the antiderivative of cotangent, you'll be like, oh yeah, the antiderivative of cotangent is the natural log of sine. It's actually the natural log of the absolute value of sine of x, but okay. Right, antiderivative is just undue derivatives. So it'll come back to you. Or what about, why don't you all try to find the derivative of the natural log of x to the 4th plus x squared? I will point out, you cannot bring down any powers because it's not everything raised to a power. You can't bring, there's no natural log simplification here. You just have to differentiate it normally, for lack of a better word. Oh, that's what I was thinking about. Well, let's see, what do we get here? We get 1 over the stuff times the derivative of the stuff, which is 4x cubed plus 2x. If you really wanted to, you could do some simplifying here. Like you could factor out an x from the top and an x squared from the bottom and do some canceling. I don't think you need to. A couple other things to know. A couple other examples to do. Yeah, something gnarly like this. We want to find the derivative of the natural log of x cubed times cosecant of x over e to the 5x times the square root of x to the 4th minus 1. Okay. Most people ask a question like this on an exam. And most people would really, really appreciate it if you didn't write your answer as 1 over all that stuff times the derivative of all that stuff. You certainly could do it that way. It's terrible. the intention of a problem like this is for you to use the properties of logarithms to break it up into simpler things before you differentiate. And that's actually a more broadly a good rule of thumb. If you can simplify your function before you take the derivative, it's usually worth doing. Afterwards, we usually don't care about simplification unless you're trying to solve it equal to 0 or do something or you're asked to. But if you can simplify before, it is almost always worth doing. So what I'm saying here is I want to break this up as the derivative of the natural log of the top minus the natural log of the bottom. And I'm going to rewrite the square root of x to the fourth minus 1 as x to the fourth minus 1 to the 1/2 power. And then I'm going to break it up some more. I'm going to break it up as the derivative of the natural log of x cubed plus the natural log of cosecant of x minus, in brackets, the natural log of e to the 5x plus the natural log of x to the fourth minus 1 to the 1/2. Finally, not finally, actually, one more simplification before we take the derivative. That's why I'm writing the ddx every time, because I haven't taken the derivative yet. I'm going to write this as 3 times natural log of x plus the natural log of cosecant of x minus the natural log of e to the 5x is just 5x. And minus distributes here, I get minus 1/2 natural log of x to the fourth minus 1, bringing that 1/2 down in front. Couple observations here. I feel like you could have maybe skipped 1 or 2 of these steps, because what you see when you have a natural log of some gross thing like this with a bunch of factors is all the factors in the numerator end up with positive coefficients. All the factors in the denominator end up with negative coefficients. And then we can bring down the powers. So if it were me, I probably would have started off by writing this as the derivative of the natural log of x cubed plus the natural log of cosecant of x minus the natural log of e to the 5x minus the natural log of x to the fourth minus 1 to the 1/2. I think that's a reasonable first step. And then the next step would be to bring down the powers. And then finally, we get to take the derivative, right? All of this was simplification. So we had to write this derivative symbol every time. And now we're actually going to differentiate this whole thing and get 3 times the derivative of natural log of x is 1 over x. The derivative of the natural log of cosecant of x is 1 over cosecant of x times the derivative of cosecant of x, which is negative cosecant of x times cotangent of x, which will end up being negative cotangent. Interesting. Minus 5 minus 1/2 times the derivative of this is 1 over x to the fourth minus 1 times 4x cubed. And yeah, it's kind of terrible. But that's definitely what you are expected to do when you see a function like this, where it's the natural log of a whole bunch of garbage.
How then e to the 5x becomes 5x.
So let me ask you a different question. So what is log base 2 of 8? Mm-hmm.
2 to the 30.
Right. 2 to the x equals 8. So x equals 3. So when I say natural log of e to the 5x, we have to remind ourselves that the natural log here is really the log base e. And so what we're saying here is that if we set that equal to, say, y, we're saying then that e to the y equals e to the 5x. So the y has to equal 5x. The more shorter way of saying this is that when you take the natural log of e to the something, the natural log function and the e to the something function undo each other. Don't say cancel, say undo each other, and then you're left with whatever you've got. Or you could even go, I want to bring that e to the 5x. I want to bring that 5x down in front. And you get 5x times the natural log of e, but the natural log of e is just 1. You need 5x.
Yeah.
But no, thank you for asking, because you probably weren't the only one who's like, how do you do that?
So, and like, for demonstrate explain how the inverse of cosecant became like.
So I want to be super duper clear. I don't have the inverse of cosecant anywhere. When you say, what are you referring to when you, what thing are we looking at when you're saying inverse of cosecant?
Wait, the ln of cosecant of x,
Mm-hmm.
and then it became, so you get how do you find how do you find the derivative of cosecant? That's what I meant.
So the derivative of cosecant is negative cosecant of x times cotangent of x. And the way we find that, I don't want to go through all the trig derivatives right now because we have talked about them at some length, but I'll remind you of this one derivative cosecant of x. We can write as the derivative of the reciprocal of sine of x. And then we use the quotient rule and say that it's the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, all divided by the denominator squared. And then we write this as negative cosine x over sine squared x, which is negative 1 over sine x times cosine x over sine x, which is equal to negative cosecant of x times cotangent of x. That's how we derive the derivative of cosecant of x. And I would encourage any of you to do the other three reciprocal functions, secant, tangent, and cotangent. I should take quotient functions really in the same sort of way. But it is something you're expected to memorize. So I'd encourage all of you also to memorize the derivatives of the trig functions. They are not going away. They definitely show up in 21B, a non-zero amount. They definitely show up in 21C, I'm pretty sure a non-zero amount. So they're not going away. Take the time to memorize them. Take the time to know them. Really. Memorize is not a strong enough word. You shouldn't just memorize these derivatives. You should know them in your heart. Let's see here. So the rule, so let me actually, I need to forget the okay, good, both good questions here. So the first one here, when I'm using for simplifying the natural log of x to the fourth minus 1 to the 1/2 as 1/2 times the natural log of x to the fourth minus 1 is one of the logarithm rules, which I will remind you of right now. So there are 3 rules for simplifying logarithms that everyone should be aware of, or I'm going to make you all aware of, which are the following. So the product rule for logs, and we do say for logs because we have a regular product rule for derivatives, is that the log, take your pick of the base, the log base b of x times y is equal to the log base b of x plus the log base b of y. We have a quotient rule for logs, which says that the log base b of x divided by y is equal to the log base b of the top thing minus the log base b of the bottom thing. And finally, we have a power rule for logs, which says that the log base b of x to a power is equal to that power times the log base b of x. Or as we often say, the power comes down in front. A couple ways to think about this. So here's a couple examples just to help you believe that it's true. The log base 2 of 4 plus the log base 2 of 8. Log base 2 of 4 is 2 because 2 squared is 4. Log base 2 of 8 is 3 because 2 to the third is 8. And 5 is equal to the log base 2 of 4 times 8. 4 times 8 is 32. 32 is 2 to the 5th power. And log base 2 of 32 says 2 to the 5th power equals 32. And then if you believe that the product rule works, then you also kind of have to believe that the power rule works for the same sort of reason. If I take the log base 2 of 2 times 2 times 2 times 2 times 2, well, I could break it up as the log base 2 of 2 plus the log base 2 of 2 plus the log base 2 of 2 5 times, which I really don't want to write 5 times, but I guess I'm going to. And that's going to be 1 plus 1 plus 1 plus 1 plus 1. Or you could see that I really have the log base 2 of 2 to the 5th. And then that's going to be the same as 5 times the log base 2 of 2, which is 5 times 1, which is 5. So these are some again, not proofs that these rules work, but examples of them working. So that's how I was able to bring that 1/2 down, is that I had a power rule there. And then the other question was, why didn't I differentiate the coefficients? Cool. So here's what I would say, and here's kind of the difference. So it'll make me go away. So it's kind of the difference between taking the derivative of 5x to the 4th versus the derivative of 5 plus x to the 4th. The derivative of 5 plus x to the 4th, well, 5 is all on its own here, and the derivative of a constant all by itself is just going to be 0. And then the derivative of x to the 4th is going to be 4x cubed. On the other hand, I bet everybody can tell me that the derivative of 5x to the 4th is what times x to the 3rd? Right, 20 times x to the 3rd. But really what's happening there, and again, we're all using this rule without actually thinking about using it, is that the derivative there is really 5 times the derivative of x to the 4th. It's the constant multiple rule. It says if you have the derivative of a constant times a function, it's equal to the constant times the derivative of the function. But nobody writes this. We just say, oh, in fact, nobody writes this either. Nobody writes 5 times 4x cubed. They just say, oh, I get 20x cubed. But the process is still the same. If you have a constant times a function, then the derivative of, say, I don't remember which one we were looking at there specifically here. The derivative of, say, oh, yeah, okay. I forgot what examples were. But for example, the derivative of 6 times e to the x squared, that 6 is a constant multiple of a function. It's going to be 6 times the derivative of e to the x squared, which is going to be e to the stuff times the derivative of the stuff. Or if I have the derivative of, say, 5 times the natural log of x cubed minus 3, that's going to be, well, I have 5 times a function of x, and the 5 hangs out, and the derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff, which is 3x squared. Now, if I was going to rewrite either of these, I would definitely rewrite this one as 12x times e to the x squared. I would certainly rewrite this one as 5 times 3 is 15x squared over x cubed minus 3. But the bigger picture point here is that constant multiples hang out. Sometimes they get changed because we multiply them by another constant, but sometimes they don't get changed, right? They just hang out and then they're 5 times whatever your derivative is. Good questions. Thank you. Okay. Logarithm. Yeah, not there yet. Sorry, I got papers everywhere as usual. And that was a good question too. Let's see here. Oh yeah. What about, what about paper that doesn't have things on it already? Sorry, I forgot to bring all my paper with me, so I was using the backs of some things, but these have backs that are printed on, so let's not use those. It'd be very challenging to read what was written. That's good to just carry a bunch of paper around in your bag. What about different bases? Have you talked about in class like the derivative of like 2 to the x? Or the derivative of log base 3 of x? Well, you probably will at some point, so we should talk about it. It's not too terrible. Let's talk about the derivative of, sure, log base 4 of x. And there's always, it feels like, numerous ways to get there. Probably the easiest way to get there is to rewrite this using the change of base formula. So that actually, there is one other logarithm formula I should make you aware of. So we'll come back to this in a second. The change of base formula. Which I would say we kind of express in maybe 3 different ways. So if you want to find the log, how am I going to write this? Sure. The log base b of x. Like if I wanted to find like the log base 3 of 17. Many older calculators, at least newer ones, probably you could find a log base whatever button. Most calculators have like a natural log button and a log base 10 button and no other bases. So how do you deal with something like log base 3 of 17 if you don't have a log base 3 button? You use the change of base formula. You say, okay, let's actually just derive it. Let's say that this is equal to y. Let's rewrite this as an exponential equation. B to the y equals x. And let's take the log of both sides. Which base? Whatever base you want. Natural log meaning log base e, or log base 10, or log base anything. Let's go very general and just say it's log using the base a, where a can represent any positive number that's not 1. If I take the log base a of both sides, I get log base a of b to the y equal to log base a of x. And then I can use the power rule, bring that y down in front, and say y times log base a of b is equal to log base a of x. And then finally, dividing by log base a of b, I get y equal to the log base a of x over the log base a of b. Rewriting the log base b of x as a quotient of 2 logarithms with whatever base I prefer. So I will just expand this a little bit. I would say that my change of base formula is that log base b of x is equal to either log base a of x over log base a of b, if you want to be very general. My default would be to say natural log of x over natural log of b. But it might also be useful to think of it as log base 10 of x over log base 10 of b. But literally, you could use base 2 or base 7 or base whatever makes sense to you. The thing I like about this formula is that when you read log base b of x, it is written so that the b is in a subscript, right? It is literally physically lower than the x. And the thing that's lower ends up in the denominator, and the thing that's higher ends up in the numerator. That feels very convenient to me. Here's one example of how this is useful, other than this. If I wanted to find log base 4 of 8, instead of doing this whole thing where you set it equal to x and then rewrite it as an exponential thing and then rewrite both things as powers of 2, you can observe that 8 and 4 both have a common base of 2. Let's use the change of base formula to write this as log with the base we want, log base 2 of 8 over log base 2 of 4. But log base 2 of 8 is 3, and log base 2 of 4 is 2. And there's your answer. Log base 4 of 8 is equal to 3 halves. Or expressed a different way, 4 raised to the 3 halves power is equal to 8. Cool. So why is this useful? Well, in this context, we can rewrite log base 4 of x as the natural log of x divided by the natural log of 4. Here's an important question. Do I need to use the quotient rule here? If I'm asking it, the answer is probably no. That's not generally. If I'm asking it, the answer is probably it's not going to be the thing you might think it's going to be. Let me show you another example before I finish this block. If I wanted to take the derivative of, say, x cubed over 5, I don't need to use the quotient rule. I could. It's more work than I want to do. I could totally write this as the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 0, over the bottom squared, and then write this as 15x squared over 25, which reduces to 3x squared over 5. Or I could do the smart thing and think of this as the derivative of the constant 1/5 times the function x cubed. The 1/5 hangs out, and the derivative of x cubed is 3x squared, which I could totally then write as 3x squared divided by 5. Same answer, much less work. So whether you're multiplying by a constant or dividing by a constant, you're still really multiplying by a constant. It's just when you're dividing, you're multiplying by the reciprocal. So whenever you're dividing by a constant, you don't need to use the quotient rule. You need to rewrite this. And we are definitely dividing by a constant here. It's not a nice constant. Natural log of 4 is, I don't know, like 1.38 or something. So we're not going to write that though. We're going to leave it as natural log of 4. We're going to write this as the derivative of 1 over natural log of 4 times the natural log of x. And just like we've seen a few times now, the derivative of a constant times a function, the constant gets to hang out. And the derivative of the natural log of x is 1 over x. And then people would normally write this as 1 over x natural log of 4. And more generally, you're taking, oh, the paper everywhere. Sorry, I know. Ah, geez, oh my goodness. Can't do it. Okay. More generally, you would maybe want to see the thing I just wrote. Yeah, okay. Generally, the derivative of log base a of x is equal to 1 over x times natural log of a. This is true even if your base is e. Right? The derivative of the natural log of x is 1 over x times the natural log of my base. The natural log of e is just 1. So this is actually the more general version of the formula for the derivative of a logarithm, but this is the one we typically remember. Cool. Cool? I don't know, cool, maybe. Interesting at least. Cool is always relative. I think it's all kind of cool. So then we can ask even worse questions. We can ask even more complicated questions. Like, can I keep the papers just don't want to stay where I want them to stay. Like, for example, if f of x is equal to the log base 7 of x to the 6 plus 9, what's f prime of x going to be? Here's the way I would say this in my head. The derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And the derivative of the log base 7 of some stuff is going to be 1 over the stuff times the derivative of the stuff. And then I also have to divide by the natural log of 7. So I'm going to say that this is going to be 1 over the stuff times the derivative of the stuff, and also dividing by the natural log of 7, which is maybe not the most compact way of writing it, but it's the way that I'm saying it in my head. So it's the way I'm going to write it for you to see. But then if I was writing this like a person that wanted to save a tree, I would write this as 6x to the 5th over x to the 6 plus 9 times natural log of 7. Why don't you all try finding the derivative of this function? G of x is going to be log base 2 of, ooh, do I want to make it a little bit harder? No, I don't. Of x to the 4th plus tangent of x. A little bit harder there. Try that one. Try finding g prime of x using the same sort of idea. Let's do one of those too. All right. So I'm going to try and do this in one step without writing it. No, I'm not. I'm not, definitely not. 1 over the stuff times the derivative of the stuff, and the derivative of x to the 4th plus tangent of x is 4x cubed plus, everybody. Awesome. And then divided by another natural log of 2. And yes, I could probably put this all together as one lovely fraction. Do you make sure that in your denominator, if you're gonna write it as one piece, it is all of this x to the fourth plus tangent of x in parentheses multiplied by the natural log of 2. All of that has to get multiplied by natural log of 2. All right. We asked about logarithms with different bases. What about exponential functions with different bases? Well, the good news is the pattern is very similar. And we'll discuss it as soon as we do an example. And there's like, people do this weirdly. There's a few different ways of doing this. So what about the derivative of 4 to the x? Yeah, I'll show you both ways. I'll show you the way I learned it, which I kind of am partial to, and I'll show you the other way that sometimes people talk about it. So one way of doing this is to write y equal to 4 to the x. And then we're going to find the derivative of y by taking the natural log of both sides. This process, which isn't super necessary here, is the process of logarithmic differentiation. You take the natural log of both sides of your expression and then simplify one of the sides using properties of logarithms. Sometimes people do this when you have something that doesn't require it. Like someone might give you y equal to some really, really gross fraction and then say use logarithmic differentiation to make that really gross fraction less gross. I can do one like that if we want to, but it's not necessary there, I think. So take the natural log of both sides. And then the whole reason for taking the natural log of 4 to the x is so that we can bring the x down in front. The natural log of y is equal to x times the natural log of 4. And now we can differentiate both sides. I'm going to remind you every time, I mean, not every time, but many times. In our framework here, y is always a function of x. It is explicitly a function of x here. Y equals 4 to the x. So when we differentiate, we are using implicit. We are thinking, oh yeah, y is some stuff. So when I differentiate both sides, the derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of the stuff. On the right-hand side, be careful here. The right-hand side's derivative is easier than you might think it is, even though you might want to make it complicated. Let me ask everybody a quick question. What's the derivative of 7 times x? Okay, I'm going to ask a slightly sillier question. What's the derivative of x times 3? Still 3. All right, just because I changed the order I multiplied the things, it didn't change the fact that I still have a constant times x. Even if that constant's super funky. Like, what's the derivative of x times e? Just e, right? E is a constant. So the derivative of a constant times x is just the constant. Okay. Drum roll, please. What's the derivative of x times natural log of 4? Natural log of 4. Natural log of 4 is a constant. Even though you might not always, it might be more challenging to see this as a constant because it looks like something that we more associate with being a function. The natural log of 4 is a constant. E to the third is a constant. If you don't see your variable in there, which is x, thing is a constant. Or y, I guess y also counts as a variable. Solve for dy dx. Dy dx equals y times the natural log of 4. And then replace y with what it's equal to. And you get that dy dx is equal to 4 to the x times the natural log of 4. Or I should say that the derivative of 4 to the x is 4 to the x times the natural log of the base. And I will make the quick connection here that just like for logarithms with different bases, we end up dividing by the natural log of the base. For exponential functions with different bases, you end up multiplying by the natural log of the base. Let me point out a different way of approaching this because some people will do this a different way. An equally good way is to rewrite y equal to 4 to the x as e to the natural log of 4 to the x. If you ever want to rewrite something, have it be the same, write e to the natural log of it. You haven't changed anything. I mean, you've changed something, but like it's still equivalent. So then I can use my logarithm rules and say, oh, I have the natural log of 4 to a power. And that x power can come down in front of the logarithm. So now I can write that y is equal to e to the x times natural log of 4. And we know, using the chain rule, how to take the derivative of e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. What's the derivative, again, of x times natural log of 4? Right, good old just natural log of 4. If you really want to make it extra clear, you could say 1 times natural log of 4. And now we're going to roll it back a little bit. I'll remind you all that we just did this whole thing here. E to the x times natural log of 4 is the same as e to the natural log of 4 to the x. Still times natural log of 4. And then e to the natural log of 4 to the x is just 4 to the x. Oh, look, the answer is the same. Some people really like doing it this way. It's not my jam, but that's okay. If you like doing it this way, that's totally fine. Whichever way you want to do it, the general, and really what I should say is for ones that are simple like this, you don't have to really do this. You can just memorize that the derivative of some different base to the x, generally, the derivative of a to the x is equal to a to the x times the natural log of a. And I suppose I owe you a caveat on the previous logarithm formula here. Over here, I should have said on this previous page, I should have pointed out that a needs to be positive and not equal to 1. Because you can't take the natural log of a negative number or 0. And if you took the natural log of 1 here, you'd be getting division by 0. It's really because log base 1 doesn't make sense, and log base negative number is not defined. Same deal. Oops, disappearing pages over here. Same deal over here. Your base, whenever you're talking about bases, whether it's exponential functions or logarithmic functions, you should always imagine your base as being positive and not 1. And again, not 1 here, not because it's not allowed, but because 1 to the x isn't an exponential function. 1 to any power is always 1, so it's just a constant. So we don't include it because it's just not part of it doesn't even be part of the crowd, right? It's like this other thing. Okay, so just like with any derivative we learn, there's always the chain rule version of it. So if instead of saying what's the derivative of like 3 to the x and getting 3 to the x times the natural log of 3, one could ask what's the derivative of 3 to the x to the 7th plus 9x plus 2. And you could take the long road. You could say, okay, I'm going to write it as e to the natural log of the stuff and then do the whole thing. In fact, I will this one time. I'm going to write it as e, the derivative, because I haven't taken the derivative yet. Do me the favor, please. Do yourselves the favor, please. If you're just simplifying your expression, still write the ddx. You're not taking the derivative yet, so you still have to write the symbol that says you need to take the derivative. Or if it's different, if it's phrased like you're given f of x equal to this thing, if you're simplifying it, say f of x equals, f of x equals, f of x equals until you get to the place where you're done simplifying, and then write f prime of x equals and take the derivative. But make sure if you're just simplifying, you're not calling it the derivative because that's not what it is. And so here, I'm still taking the derivative of e to the natural log of 3 to the terrible x to the 7th plus 9x plus 2. And again, we're going to bring that down in front. We're going to get the derivative still of e to the x to the 7th plus 9x plus 2 times the natural log of 3. And now we're in a position where we can actually take the derivative. The derivative of stuff is going to be e to the same stuff. So e to the x to the 7 plus 9 plus 2 times natural log of 3 times the derivative of all that stuff. And the derivative of all that stuff, well, it's going to be the derivative of this, and the constant multiple gets to just hang out. So it's going to be 7x to the 6th plus 9 times the natural log of 3. And then I'll remind everybody, because we shouldn't leave it like this is really the same as 3 to the x to the 7 plus 9x plus 2. So I should really write my answer as 3 to the x to the 7th plus 9x plus 2 times 7x to the 6th plus 9 times the natural log of 3. I don't think you need to show this work. I think you can get away with saying the derivative of 5 to the x to the 4th plus, sure, cosine of x. We know the pattern. We know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. We know the derivative of some other base to the stuff is that base to the stuff times the derivative of the stuff times the natural log of that different base. Or e, if it's e, right? You could throw in the natural log of e at the end there. You don't need to. You shouldn't, but you could. So we can say the derivative of this is going to be 5 to the stuff times the derivative of that stuff, which is 4x cubed minus sine of x, times the natural log of my base, which is the natural log of 5. And no one's going to blink an eye if you don't show any more work than that there, because they're, unless they ask you to, right? But there's kind of an expectation that this is a formula that's relatively, I don't know, straightforward, for lack of a better term. So I'll just point out, in some sense, there are kind of 8 rules for taking derivatives of exponential functions and logarithmic functions, but that's really a lie. There's really only 2. Let me show you what I mean. I'm going to write down the high level rule, and then we'll talk about the kind of simplifications of it. So here are the most challenging rules at their worst. I don't know. Yeah. Okay, I'm going to do the thing, instead of writing stuff, even though I like to write stuff, I'm going to write u instead. So the derivative of a to the u of x. So the derivative of a to the stuff, I'm still going to say stuff. I can't not say stuff. Is going to be a to the stuff times the derivative of the stuff times the natural log of a. And the logarithm version, the derivative of the log base a of some stuff is 1 over the stuff times the derivative of the stuff divided by the natural log of a. I know I'm saying divided by the natural log of a, and I'm writing 1 over the natural log of a. They mean the same thing. Times 1 over natural log of a is the same as divided by the natural log of a. This is the most general version of all the other formulas I'm about to write. So then we have the nicer version of this, which is that the derivative of e to the stuff is e to the stuff times the derivative of the stuff times the natural log of e, if you like, but we don't. And similarly, the derivative of the natural log of some stuff is equal to 1 over the stuff times the derivative of the stuff. And then we also have the non-changeable versions of these formulas. If you have just the derivative of a to the x, it's a to the x times the natural log of a. And the derivative of log base a of x is 1 over x natural log of a. Oh, I wrote the wrong thing there. Don't let me get away with that. This should be a natural log of a. Woo. Finally, the basicest version of these, the derivative of e to the x is e to the x. And the derivative of the natural log of x is 1 over x. But really, This most basic version, the derivative of e to the x equals e to the x, is just this formula where your base is e and your stuff is x. And the derivative of my base to the stuff is e to the x times the derivative of x times the natural log of e, which is e to the x times 1 times 1. So really, technically, you only need to know these top two formulas, but honestly, these bottom ones are the ones that you remember, and then you kind of just use the stuff version of them when you have to. Let's see, what time is it? Okay, what day is it? Thursday? Thursday, okay. Yeah. Yeah, we'll do one of those. So the last kind of thing when it comes to these exponential style things is when your base and your exponent both have a variable in them. For example, kind of a classic example, I want to find dy dx for the function y equal to x to the x. None of your rules apply here. That's not true, but it's kind of true. All the rules still apply, but just we don't have a constant in our base, so we can't use the rules we just talked about. And we don't have a constant as our exponent, so it's not like taking the derivative of x to the third and saying it's 3x squared. You can't bring your power down and subtract 1. There is a stupid formula for functions like this where it's f of x to the g of x. No one should memorize it. Ever. It's terrible. Don't waste space memorizing something in your head when you can just use the same process that you've already learned. So let's use the same process. I want to differentiate something where I have problems with my exponents. So I'm going to start by taking the natural log of both sides. So the natural log of y equals the natural log of x to the x. Bring down the exponent. So the natural log of y equals x times the natural log of x. And now we're going to differentiate both sides. By the way, hopefully you all are seeing why we spent some time talking about implicit. Implicit comes up over and over and over again. We are often saying y equals some stuff, then you've got a function of y, and then you're differentiating the function of y. So here, the derivative of the natural log of y is 1 over y times the derivative of y. Unlike the previous problems where we had x times natural log of 4 and the derivative was 1 times natural log of 4, here we have x times a function of x, and we have to use the product. So the derivative on the right-hand side is going to be the derivative of x, which is 1, times the natural log of x, plus x times the derivative of the natural log of x, which is 1 over x. These next two steps you could condense into one, but I will show both of them. The first step is to multiply both sides by y. So y prime is equal to y times the natural log of x plus x times 1 over x does simplify to 1. Although I think you can skip writing y there and write it as what y is equal to, which is x to the x. So y prime is equal to x to the x times the natural log of x. And that's your derivative. So the derivative of x to the x is equal to x to the x times the natural log of x plus 1. And you can do this for any sort of expression where you've got an exponentially kind of thing, and your base is variable and your exponent is variable. Let's do one more example of that. I will point out the process is always the same, like 4 steps. So we're going to start with given f of x equal to, sure, x squared plus 3 to the sine of x power. Looks reasonably terrible. Find the derivative. And honestly, I don't want to use f. I want to use y because it's easier to write natural log of y than natural log of f of x. So let's just say we're going to start with y equal to x squared plus 3 to the sine x. I can choose to call things whatever I want to. I will point out, you do need both sides of this equation. Because to deal with something like this using the process we're talking about, you have to be able to take the natural log of both sides. So then we're going to take the natural log of both sides. And the reason or the motivation for this is that that variable in my exponent, I really would prefer it is not a variable in my exponent. I would prefer I don't have an exponent. And taking the natural log of that then allows me to bring the thing in the exponent out of the exponent and have sine of x times the natural log of x squared plus 3. And then we take the derivative of both sides. The left side derivative is always going to end up being 1 over your stuff times the derivative of your stuff, which is 1 over y times y prime. On the right-hand side, for ones like this, it is always going to use at least the product rule, maybe also the quotient rule, maybe the chain rule. So here, derivative of sine is cosine of x times leave the other thing alone, plus switch it up, leave the sine of x alone. And the derivative of the natural log of some stuff is chain rule, 1 over the stuff times the derivative of the stuff. Okay, I think we can skip the intermediate step here. I'm just going to go ahead and write. I'll write it back in a second. All right, y prime equals y, which is x squared plus 3 to the sine of x power, times all of this stuff here. Cosine of x times the natural log of x squared plus 3, plus I would probably rewrite this as a fraction. I would write it as 2x times sine of x, all divided by x squared plus 3. If you don't love skipping that step, you're totally welcome to write the middle step, which is y prime equal to y times all of this stuff here. But I think, especially with how long these are, you typically can skip that step if you're comfortable. Oh yeah, y is just going to be whatever y was. Okay. How much time? We got 10 minutes. So many other things to say. I saw an interesting question on one of the discussion sheets for Grosvenor's class, which I thought was worth, not that exact problem, but worth going over something similar. So let's say we've got the following situation. And really because we didn't really talk about it, this is why I'm actually going over it. Let's say we've got, so y equal to some function of x satisfies the following equation. X squared plus y equals y cubed minus x. I want to find y prime and y double prime evaluated at the point 0, 1. And I honestly can't, I feel like we talked about using implicit at a certain point, but I don't actually remember if we talked about it, so we're going to talk about it right now. Also, we definitely didn't talk about the second derivative implicitly, so we should talk about that. All right, so to find y prime, differentiate both sides. So differentiating this equation, let's write it again, x squared plus y equal to y cubed minus x. The derivative of x squared is 2x. The derivative of y is y prime. The derivative of y cubed is 3y squared times y prime. And the derivative of x is 1. Normally, if I was just asked to find the derivative at the point 0, 1, or find the slope of the tangent line at the point 0, 1, or find the equation of the tangent line at the point 0, 1, at this juncture, I would just plug in 0 for x and 1 for y. Let's do that. So I plug in x equal to 0 and y equal to 1. I'm going to get 2 times 0 plus y prime equal to 3 times 1 squared times y prime minus 1. And that's going to simplify as y prime equals 3y prime minus 1. So y prime minus 3y prime is negative 2y prime equal to negative 1. So y prime equals 1/2. And if that was the end of the story, that's what I would do. Like, so if they just give you an implicitly defined function and ask you to find the slope of the tangent line somewhere, take the derivative of both sides and then immediately plug in your point. and then solve for y prime. However, if we have to find the second derivative, you have to actually know the first derivative before you can find the second derivative. So we actually have to do the algebra here. So solving for y prime, I'm going to bring all my y primes to the right side. I picked the right side because most things will be positive if I bring all my y primes to the right. I would rather have 3y squared y prime minus y prime equal to 2x plus 1, as opposed to y prime minus 3y squared y prime equal to negative 2x minus 1. It's just nicer to look at. Factor out a y prime from the side the y primes are on. So you've got y prime times 3y squared minus 1. Finally, divide by that to get 2x plus 1 divided by 3y squared minus 1 equal to y prime. And then the kind of bummer is that to find y double prime, you almost always have to use the quotient rule. There's really, I mean, not the quotient rule is not the worst thing in the world. It just always feels like there's a lot of stuff to write. So it's nice to avoid it when you can, but you can't always avoid the quotient rule. So y double prime. So we're taking the derivative of 2x plus 1 over 3y squared minus 1. Remembering that y is still a function of x. Okay, so quotient rule time. Bottom, 3y squared minus 1 times the derivative of the top, which is just 2, minus the top, which is 2x plus 1, times the derivative of the bottom. Here's where we have to be careful. The derivative of 3y squared minus 1 is going to be 6y times the derivative of y. All divided by 3y squared minus 1 squared. The good news here is that we were asked to find y double prime at a specific point. So we don't have to do the terrible thing that we're going to do anyway. But if we were just trying to answer the question, we would then say, well, y double prime at x equals 0, y equals 1. If I start plugging in, watch. Y double prime at 0, 1 is equal to 3 times 1 squared minus 1 times 2 minus 2 times 0 plus 1 times 6 times 1 times, what's y prime? At 0, 1. We did it already. It was 1/2. And then divided by 3 times 1 squared minus 1 squared. And you would get something. You get 3 minus 1 is 2, 2 times 2 is 4, 0 plus 1 is 1, 1 times 6 times 1/2 is 3, divided by 3 times 1 is 3, minus 1 is 2, 2 squared is 4. So you end up with 1/4. Cool. On the other hand, if someone says actually to find y double prime, it's kind of gross. You have to go back and say, well, yeah, we should do that because we have enough to do that. So just to kind of point this out, I keep getting out of frame here. I'm sorry. So if this is what my y double prime is equal to, well, y double prime should not depend on y prime. And it doesn't have to because we know what y prime is. Y prime is 2x plus 1 over 3y squared minus 1. So to finish this, you have to do the terrible thing where you say, well, I've got 2 times 3x squared minus 1 minus 6y times 2x plus 1 times y prime, which is exactly 2x plus 1 over 3y squared minus 1 over the same denominator, 3x squared minus 1 squared. It's actually not too awful here, but every time there's a y prime in your answer, you have to plug in what y prime is equal to. And then, yes, you could simplify this. That should be I feel like I made an error somewhere here. I feel like a y turned into an x accidentally, and that's not good. Yeah, sorry, this x down here somehow, ooh, yeah, be careful, James. That should be a 3y squared minus 1. And that should be a 3y squared minus 1. Sorry about that, that is terrible. I will say that does kind of point out how easy it is to accidentally have an x turn into a y or a y turn into an x. So definitely be careful when you're writing these things. It's really, really easy for things to accidentally, like a 3 can turn into a 5 super easily for me. An x can turn into a y without too much not paying attention. So just be careful when you're writing. It's easy for things to transform into other things. All right. Next class, I guess we'll talk about the inverse trig stuff because we didn't get through. I will point out that the inverse trig derivatives, the process is very, very similar to what we just talked about, where you're taking the natural log of both sides and then differentiating both sides and then solving for y prime. The only difference is instead of taking like the natural log of both sides, you're taking like the tangent of both sides. So for example, I know I said we're done, but we're not done. If you're trying to find the derivative of the arctangent of x, you would rewrite this as tangent of y equal to x, and then you would differentiate both sides. The derivative tangent of the stuff would be secant squared of your stuff times the derivative of your stuff. Derivative of x is 1, and then you solve for your stuff. And then you use some triangle magic to figure out what secant squared of y is equal to. Or a trig identity. But that's next time. Cool. Okay, fine. It's 1/1 plus tangent squared of y, which is 1. Cool. There's one of them. There's 6 of them. There's really only 3 of them. Because the derivative of arc tangent is almost the same as the derivative of arc cotangent. The derivative of arc sine is virtually the same as the derivative of arc cosine. And the derivative of arc secant is virtually the same as the derivative of arc cosecant. And I would encourage you all to say arc instead of inverse. You can certainly say inverse cosine or arc cosine, but the issue you might have with inverse cosine is you might accidentally incorrectly think of it as 1 over cosine, which it is definitely not. 1 over cosine is secant. Inverse cosine or arc cosine is the function that undoes what cosine does. Cosine of pi over 3 equals 1/2. Arc cosine of 1/2 equals pi over 3. I know it's a lot to say at the end of class, but didn't want to not say anything about it. So next time we'll talk more about that.